Okay, you can take a photo. Okay, so you can see we talked about the moments in order. We started with the 0th moment, which we called the monopole, right. Then we talked about the first order moment, which we call the dipole, which is the most common one, right. And then we talked about the second order moment, which we call the quadrupole, and so on. So we see a relationship which is dependent on the power of R. And now we are going to go further with this explanation. So, electric and
I have a question.
Yeah.
In a monopole, its field, its hypothetical field, should be generated in a plane, and that's why it decreases with.
You're still stuck in the monopole, but we are not working with the monopole.
Yeah, but I'm just making an argument. And in a dipole,
Yeah.
we know that its field propagates in 3 dimensions, and that's why it decreases by 1 over r cubed.
Yeah.
But what exactly is the case of the quadrupole?
Right.
Why does it decrease with r to the power 4?
Okay, so there are.
It has no dimension to.
Yeah. So there is some logic to this, and we are going to go into that. Okay.
So are they like? Is this the thing that caused us to think about higher dimensions?
Wow, you're going too far. I think we are still in the real world. Yeah, we are in the real world so far. So let's try to explain this. Electric and magnetic multipole moments can be calculated using electrodynamics, as you know, and which also uses the concepts of quantum mechanics, right. And therefore, we will be treating the multipole moments in an operator form and calculating their expectation values for various nuclear states. Again, you know the concept of operators, right. You know the concept of expectation values, right. Now, we will not use it too much, but if you want to go into further detail, so that is how you approach it. Okay. Again, this can be explained more in detail in a course which will be particularly on electrodynamics. Okay. So, these expectation values even then can be directly compared with the experimental values that we can measure in the lab. Like everything that we have been studying so far, you see there is always a theoretical component to it and there is a lab component to it. So, like we discussed the formulas give us the mathematical explanation for something, and then we also discuss about the possible experiments that lead to those values, even starting with the radius, for example, right. We talked about some formulas, right, and then we talked about some measurements, like we said, and then I showed you this table that we will be using from time to time at the back of your book, and I also told you there are more updated tables also that you can see at various websites, like I told you the NIST website, I told you the IAEA website, I told you these are some well known, the CERN website, for example, these are some well known sources of authentic values, and scientists spent years and their lifetimes in trying to determine these parameters that we can easily access. So, of course, experimental values and theoretical values normally they have to of course match each other, and then we can say that the explanation we are trying to give is valid. So, what we are speaking about has been tested or has been both theoretically and experimentally, and there is always some logic behind what it is. Of course, you can go further and you can try to improve it, right, or you can, there are different ways to do research. For example, one is you try to do something that has never been done before, but you always have to base it on previous work, right, on the foundations that you have. And the second is you try to improve something that has already been done, right. So, for example, whenever you do something theoretically, it does not hold value unless an experimental verification is available. And as you know, the famous Nobel Prize is only given when a theory has been proven experimentally. So, Abdus Salam got his Nobel Prize. He had proposed the theory before, and he got the Nobel Prize when it was tested later in an experiment and proven to be correct. But there are scientists, for example, Stephen Hawking, who never got a Nobel Prize, although his theories are very impressive, but because no one so far has been able to perform an experiment to verify that, right.
Similarly, Einstein didn't get a Nobel Prize in general relativity.
Yes, although that was one of his main works, he got the Nobel Prize for the photoelectric effect because the photoelectric experiment had been performed and his theory had been verified. So, it is very important to work both, to have both a theoretical understanding and an experimental understanding. Even if you are a theoretician, you need to understand how experiments work, because if you do not understand them, you will not be able to propose an experiment to verify that the theory that you are making. And Abdus Salam proposed the experiments that would verify his and there was a biography about him in which he talks about when he was a student and his professor sent him to take an experimental practical lab course, and he did not have an interest in doing that. He was a mathematician basically. His first degree was in mathematics, right. So, when he went to the lab, in the lab we have to take several readings of the same thing. He thought this was a waste of time, and he asked the teacher, why do I have to take so many readings, because all you need from me as the result is a graph which is a straight line. So, to make a straight line you only need 2 points. So, why do you want me to take so many readings and observations? And that is what an experiment is about, right. Why do we take so many readings and observations? An experiment requires a lot of patience, in fact. Why?
To be more precise.
To reduce the error. There is always error, there is always uncertainty for many different reasons that we start talking about from the beginning when you start studying physics, and therefore, no matter how simple or how complex your experiment is, there always will be error, and your task is to minimize that error to a level where your values that you get from that experiment are trustworthy enough to be accepted scientifically, right. And then the theory, again, mathematics is very beautiful, we all admire that and we all believe in that, but again mathematics can be manipulated in many ways. We know that, for example, at the time when the people thought in the space we had ether and so on, they used to put a constant to try to justify that. So, in every theory, in every derivation, we always use assumptions. Now, we have to justify those assumptions from time to time, and sometimes our assumptions are not, we have to change them as well. Okay. So, that is why it is very important to go both scientific, this is called the scientific method. So, the scientific method is about not accepting anything until you have proven it. Before, during Aristotle's time, he did not used to prove anything, but people respected him a lot. So, a lot of the
That's why he was wrong about most of the things that
no, but then we cannot completely discard him because he was also right about some important stuff, right?
It is just like Thomas Kuhn said that in his book, The Structure of Scientific Revolution, that just because you have got a better theory doesn't mean that the previous one is wrong.
Of course, yes. Right. So, that is why we cannot say that we have quantum physics and therefore we can discard classical physics. We cannot do that. Even Einstein himself said that if I am able to see forward, it is because I am standing on the shoulders of giants, right. So, this is an evolution, science is an evolution, and therefore, all the topics that we are studying, coming back to there, we have some mathematical explanation for them, and then we also talk about the experiments that proved those concepts, and we try to relate both. Okay, we try to understand that, but again, like you cannot expect everything to be proven in one course. Of course, each of these can be one big course, right. Okay, so let us go further. Like we talked about the fact that these properties can be proven with the help of quantum mechanics using the concepts of operators. Operators we use to represent physical quantities, right, and then we can calculate their expectation values. And on the other hand, we can devise experiments in the lab and then try to measure them and then try to match both. So let us come back to the simplest distribution, and which is current, for example, right, which gives the lowest order multipole field. We know that if there is a current flowing, there is a field, right. So that is a simple example. So a spherical charge distribution gives only a monopole which is a Coulomb